I'm going to try to highlight how to write these equations that you see on the board in front of me here. Get a full screen, and then I'll have at it. And so just going to get to mechanics of writing functions quickly and easily, 10 seconds or less with some random numbers. Then I'm going to talk a little bit about why I think we should not stress transformations early on in students' mathematical careers, high school study. And let me get a marker that's going to highlight what I'm just about to do. Let's see if that one works. It does. All right, so each of these equations, I just threw some numbers on the board randomly, and now I'm going to look at them and just create the equations and begin the process, start a conversation about particular A at this point, but let's just have at it, 5, 7. So I'm putting it in graphing form, we highlight the vertex, and then we look at from 5 to 11, 6 units of linear change, but it's 36 units of quadratic change. And that's measuring quadratic change is measured from the number 5. And 36 plus 7 doesn't take me to 30, so I get rid of it. What does take me from 7 to 30? 23 units. So if you were to put that into Desmos, you'd get that graph. So it looks like the A term of a quadratic is rise over run squared as measured from the vertex. Why that doesn't seem to be common knowledge, I do not know. All right. Now, if you can do squaring, should be able to do square rooting. Oh, very similar process. And this could be the graphic form for a square root. So x minus 8 plus 2. Let's make sure we know what a square root is. Square root of 9 is 3, so a square root is the side length of the square. So I really have area converted to side length. 8, 2, I've just done that. If I put 11 in, I get the square root of 3, and the square root of 3 plus 2 does not take me to 33. But what takes me from 2 to 33? 31. That's that equation. Doesn't take a lot to learn how to do that. A couple of days of practice, 5 minutes, 2, 3 minutes a day, 4 days in a row. You'll get a handle on that. Let your brain start to consider what's going on. Graphing form for absolute value. All right, so x minus 4 plus 7. You'll notice I've been creating zeros here. Y is 0, important for the absolute value. Smallest distance you can travel is 0. Smallest distance you can have for a square root is 0. Smallest square area you can generate, 0. All right, so let's get rid of the absolute value change from 4 to 19. Why don't I write it as 19 minus 4 absolute value? Doesn't. 15 plus 7 doesn't take me to -9, but 7 to -9, I believe, is minus 60. Okay, that's that equation. About an exponential. Well, the conversion takes, well, so this A term is what? Rise over the absolute value change in the run, which is really change in X, right? Fancy name for change in X. The A value back here, you can't see anymore for the square root. Square root, the A value, the adjuster I like to call it, is the rise over the square root of run as measured from that endpoint. All right, do I have an eraser here? Of course not. Let me grab one. I'll use it as we go along. Coming right back. Should have said at the beginning of the video, if you want to try to figure this out, pause the video, but just showing it at this point. So let's start with the most important Y value, which is 5. How do I get to 11? I add 6. The next time I don't add 6. The next time I go from 5 to 28, which is 23 units of change. And then we got to get our time. So let me write this as a function of time. How about A as a function of T? Amount as a function of time. So T minus 1900 over 1900 to 2400, 24 years. So I think I should show this conversion, because the conversion doesn't take place as a multiplication. If we put 1900 years in here, 1900, I use a subscript for years, well, the years disappear. I just get a generic 0, which could bring in the number of sheep in the town of Gill. And if this was years, and I drop in 2024, well, 124 years divided by 124 years is the number 1. I'm converting units into something else. I just thought I'd point that out. So that's the exponential, the logarithmic, and every single one of these, I've got videos that do 4 or 5 in a row, talk about the geometric implications of why we can do what we're doing. But here I'm just trying to point it out that it's a whole different way of looking at things. So we start with y equals. So how about we take the first y we see? We ask, how do you get to the next y? Looks like we're going up 47 years. Yep, I remember 1853. Yeah, some good folks are around at that point in time in New England, at least. Oh, shouldn't have said that. Log. Where was I? I lost my train of thought. Oh, first x. So x minus 2 gets our domain restriction, and so I'm picking up numbers. Change, put 9 in, you change by 7. Put 20 in, and you got 18/7 as a base. Okay, so that's that equation. Not that those are the friendliest numbers. Might have been nice if I got you a base of 3 or something, but that's how quickly you can write those with a little bit of practice. And what about a reflection? So what about a reflection here around x equals 2? All right, so I'll start with 1600. How do I get from 1600 to 1703? I remember those years. Go up 103 years. It's a logarithm. We're looking at x equals 2 again, but we're looking in the other direction. So why don't I write it backwards? 2 minus x. Now when I drop it to -3, I got 5. So let's divide by 5, make log 1, which is 0. And now I'll drop in a -10, and I get 12/5. I got a feeling if I put this equation in, Desmos is going to practice, is going to graph that for me, or some calculator, whatever you're working with. All right, sinusoids. I'll first do it as a sine function, and then I'll do it as a cosine function. At least we can see that they differ by 90 degrees. So we get a kind of a generic understanding rather than just reading it in the old text. Looks like 85 is the center of the sinusoid. I'm going up and down 5, but we'll always write it as a positive. And let's go with the sine, and I've got 1 pi, 2, 3, 4, 5, 6, 7, 3.5 revolutions, 7 pi. And that takes 1850, another good year, 53 years. And then I've got x minus 1850, using those zeros. And that will be centered at pi/2 on the unit circle, because that's what I want, max. And the sine function is a max at pi/2. I could have written it as a cosine function with very simple change, because the cosine function maxes at 0 on the unit circle, 1. So x minus 1800 is the same function, generating the same numbers. And I'll just put a quick cubic into graphing form real quick with some minimum data, just to say that there's lots of things to study here that really don't take all that long. 43 minus 160 minus 1, rate of change -5. If you want to have a little challenge, you can try to do it yourself. Figure out what's going on, but the graphing form for a cubic is y equals a x minus h cubed plus m, a multiplier times x minus h plus k. And h comes from minus b over 3a, the average of the roots. So I'm going to write a, I'm going to develop a in a minute. So x minus 43 cubed, I don't write 3's well, it's terrible. Plus some number, which in this case is -5. So again, you write that. -5 times x minus 43 gets us -100. All right. So the a term, well, I got to get from -100 up to -1. So I got to go up 99. But the linear function's taking me down. How far did I change? 43 to 60, 17 times 5, 85 units. So I got to negate that by plus 85, and cubic change from, oh, did I really do cubic change? 17 cubed. I'm just going to have to write it as 17 cubed because I don't know what 17 cubed is. Right, but that's what I changed from there to there. Guess I got to write that. Funky number. All right, so basically what I've been doing is I've been looking at multiplying functions and adding a constant. And m times 0 gets me c, and m times 1 gets me m plus c. And I was using that quite a bit here. Not in every situation, but most. All right, so here's the case against transformations. What I've noticed over my career is that students who have strong computational skills improve more quickly than students who have weaker computational skills. So I think we should be stressing improving everyone's computational skills. And how do we do that? We talk about the graph shifts 5 to the left. When I learned math, I've been learning math as an adult. When I encountered that concept as an adult, I'm like, geez, how does a graph move? It seems like an inanimate object to me. So it didn't make much sense to me, although I could see it. And I guess, the parent function, we talk about parent functions, shifting, but I think we really want to talk about change from a location. And to get a real feel for a calculation, I think you got to calculate, especially e to the x and ln of x. You got to play with numbers, right? And so speed graphing e to the x and ln of x, I didn't show it over there, but there are some videos on the channel and you can dive into that. And usually after about 5 tries, you got it down. All right, so let's look at x squared, the signature squaring process, 0, 1, 4, 9, 16, etc. Right? 0 times 0 is 0. That's the smallest, that's a minimum. You don't have any dimensions to a square, you're not getting any area. Okay, so you can pause the video as I go along here and you can try to name. So we just named this process x squared. You can try to, I've already named it. Oh, God, I've tried to do this video 2 or 3 times and I've got interrupted every single time with a phone call or a text that I had to answer. So I'm not shutting off technology right now, except for the recording. All right, so can you look at that? And then, of course, I already gave it to you. A 5 acts like a 0 now. Acts like this. So how do you turn a number 5 into a 0? You make a statement like x minus 5. And how do we get the squaring process to show up? Well, you square. Okay, so I'm not talking about shifting 5 units to the right. I'm saying I am looking at square change from the number 5. So if I was on the number line and I was at 5 and I went to 9, I really have 16 units of change because I'm squaring that run. The run is being squared using some of the vernacular that comes out of an algebra 1 class. All right, so if I move 1 unit, I square that, I get 1 unit of change. 5 to 7, 2 units of change gets me 4 units of area. 3 units of change gets me 9 units of area. All right, so what would this next one be? I think you can still see it. All right, so how would I change the preceding one into the next one? Pause the video, you think about it. I'm just going to keep talking. Well, what do I see? I don't see any change on the x's, and yet the y's. A 0 is now still 0. Okay, so, but a 1 becomes a 3, a 4 becomes a 12, a 9 becomes a 27. Yeah, it sure does look like I'm multiplying next. Yep, looks like I am. And then, of course, we've got the next one. What did I do here? Oh, wait a minute. So that was fine, right? Did I do the 3 times 3 there? No, I did the 2 times 3 here. All right, so that one is that, and this one is this. I'm not going to do this again. This will be the 4th time trying to get through this without a mistake. All right, I'm just not going to do it. All right, so that was the one that was tripled. I think I pointed you in this direction, but I got mixed up here. And then we got one more. 27 now, because this column's the same, so I must be, doing something after the squaring process. Begin with, I did something before the squaring process. That's important to talk about too. But anyway, so how do I get from 27 to 36, from 12 to 21, from 3 to 12, from 0 to 9? Well, I think you're probably right. Add 9. All right, now from you know, from earlier in the video, we talk about change. Well, let's look at change from 5 to 8. Right? Because I could have written this equation, I think. Just those two numbers, 5 to 9, 8 to 36. Yeah, I think I can do 5 to 9 like I was doing over there. Right? And then 5 to 8 is quadratic change, which is different than linear change. And I think we should write the one for students who are just beginning their study in algebra, right? Because I'm getting rid of linear change in the denominator there. Now I'm getting rid of quadratic change. 5 to 8 is 9 units of quadratic change. And how did I go from 9 to 36? I went up 27. My goodness, that's 3. There must be a coincidence here. 27 over 9. Boy, I wonder if it works for 7 gets me 36. What was it? 7 gets me 3 plus 9, right? So where the heck am I? 7 minus 5, 2 squared, 4, 12. 12 plus 9, I guess I had a 21 here. All right, yeah, I guess I could have gone over here. It's all right, so let's look at that. 9 to 21. Oh, well, that's 18 units of change. And 5 to 7 is, did I botch this now? 9 to 12, 9 to 21 is 12 units of change. I'm not doing the video again. And 5 to 7 is 2 units squared is 4. Oh, 12 divided by 4. I don't think that number's changed. Oh, boy. Sure looks like it's rise over run squared as measured from the vertex. That's the A term of an AX squared plus BX plus C model. Might be useful to know that. All right, so that was just the case against transformations that, just like I did, I just got a little practice calculating. I said, oh, I made a mistake and I had to figure it out. I think that's I think that's the major part of the learning process, is playing with numbers. Good computational skills. The students who have the stronger computational skills go up faster. So let's do both at the same time. And one last thing, just to point out some quick calculus, just because I think the conversations have to start. There's our signature, decreasing areas to increasing areas. And it's flat right there. It's flat. Why? There's no area. There's no area. And how does change occur in a quadratic? Well, let's look at zooming in on 4 gets a 16, and 4.001 gets a 16.008001. So there's 0.008 new units of area. And it really comes from a layering process. And if I increase this by 0.01, then I'm increasing the area that's hard to draw because it's such a small amount, right? 0.01 times 4 is 0.04. And that area on the right added to that area on the left. And I can see that this is an X and that's an X in calculus. Y equals X squared, the derivative is 2X. I really think that people should see that. It's not generally in the textbooks, and not the ones I've seen. And I think that's the most important thing to put in the textbook. It's not quite what Newton saw, but it's pretty close. He did a sandwich, but you know, it's a layering process. And if you add up those layers, you can get to a 5v5, right? If you add up all those layers, 2x layers with a little bit of change from 4 to 5, then you get X squared from 4 to 5, which is 25 minus 16. New 9 units of area, 9 new units of area. And I just want to put that thought in your head before you get to a calculus class, right? And if you square 0, you don't get any change. Why? Because 0, you know, how much change are you going to see? 0.001 times 0.001 doesn't give you much change because there's not much area there to begin with. Pretty hard to layer. You know, I'm standardizing the change in this dimension. The bigger the square, the quicker you're going up. The smaller the square, less quickly. All right, so there's some fodder. Oh, I was going to do one last thing with you. Boy, the lengthy video here. Same thing here. We're going to practice developing from a numerical standpoint, a little bit of exponential work. Pause the video. And you can tell I'm rushing through this. Why am I rushing through this? Because fire trucks are dead. And no, I'm rushing through it because I've been at this for a long time and I kept having to redo it. And so, oh God help me. 2 to the 0 is 1. I just answered what this function was. I hope you paused the video before I did that. So this is 2 to the x. And for folks who don't know why 2 to the 0 is 1, let's do some 2 work. 2 times 2 times 2 over 2 times 2 times 2 is 2, which is 2 to the 4 minus 3, your rules of exponents. If I add another 2 into the denominator, there is no difference. I get 2 to the 0, and if there's no difference, something divided by itself is 1. And if I were to add 1 more times 2, then it would be 4 minus 5. And if you take the time to look at the calculation, you get a half. So 2 to the minus 1 equals 1 over 2. It looks like that minus sign is really reciprocation. All right, so pause the video. I'm giving you a new table. Can you name this table based on the previous one? And I got to get my coffee. I apologize for the speed I'm doing this at. But I'm not doing it again. All right, so right now it's 0 gets us 1. 1900 gets us 1. I think we got to make that act like 0. The power of the marker. I get to write what's true. Whoa, is that a revelation? About 20 years for me. Oh, a lot of power in this thing. Okay, so now how do we get from this table to that table? That's called from this place to this place, and in math we call this displacement. I'm sorry. All right, so 1900 still gets me 1. Did I even change the table? No. Oh, I changed the years. 19 to 1830. Oh, okay, so I think I'm doing something with the x's. What am I doing? See, 70 years, 70 years, 19. Yeah, it looks like it happens. This process happens every 70 years. So I guess I got to make 1970 when I plug this in. I got to turn that into a 1, right? 19, yeah, because that's changing by 1. This is changing by 70. So how do I turn the number 70 into a 1? Geez, maybe I can do that. Let's try that. Boy, now I got years to amounts. Let's put 3100 in. Let's put 204 in. Oh, that's 140. Divided by 7 is 2. Oh, yeah. 1902 changed by 2. Oh, this is changing by 2. That's good. I like that. Let's move this without spilling my coffee because I did that. That stopped one of the videos right there. I knocked the coffee cup off the table. Had to go get a mop. How do I get from this to this? Pause the video. I did it. I did the same thing I did over there. This is the one I should have written. 2 to the x minus 1900. This is where we're at, I think. Yeah, you can tell I'm doing this on the fly. All right, so how do I get from this table to that table? I'm having a drink of coffee. Well, it looks like the y's have changed. I guess I got to do something here. So a 1 became an 8. A 1/2 became a 4. A 1/4 became a 2. It's easier to see a 2 to a 16 and a 4 to a 32. Sure, it looks like I'm multiplying that process by 8. All right, now I'm on a roll. Last one, last chance to mess this up. Don't go anywhere, coffee cup. There we go. So what's the last one? Well, it looks like the y values have changed. 2 is now 9, 4 is now 11, 8 is now 15, 16 is 23. Yeah, it sure looks like I simply added 7. Okay, so if I'm doubling every 70 years, I'm probably quadrupling every 140 years. So let's erase this and see if we can graph and do a little practice like we did over there. Right, the asymptote here. Well, it'd be hard for you to see the asymptote. All right, I mean, I'm really changing by 4. I'm really changing by 2. I'm going to change by 1. I'm going to change by a half. Right, just a little bit of play there. So, but if I gave you y equals 7, right, and I gave you 1900 gets us, I hope it was 15, yeah. 1900 gets us 15. There's an infinite way of writing these exponential functions. 2040 gets us 39. That's about 4 times bigger differentially. 2040 gets us 39. All right. Then I'm really looking at from 7 to 39 is 32 units of change. From 7 to 15 is 8. Hope we can see the quadrupling there. All right, and so if I want to write that equation, running out of room here, but I'll write it here. Y equals 7. How do I get to 15? I add 8. Next time, I don't add 8. Next time I go from 7 to 39, which is 32. Maybe you now know where the base of an exponential function comes from. X minus or t, let's go f of t here. This function is based on years. So t minus 1900 over 140. So now we're quadrupling every 140 years versus doubling every 70. All right, so that was a very quick video. And I'm sorry for the speed, but you know, I was a little frustrated here with how many times I had to do this. So I just produced it because I think it's important for getting conversations started. And when I think conversations around transformations, I have a colleague who I'm sure is a very bright mathematician, gone a lot further up the ladder than I have. And he talks about the value of transformations. And I believe him when it comes to certain parts of mathematics that I haven't studied, that he says they're important, then they're important. Okay? But I think transformations is a generalization of a process. And if we give students the generalization before they've gone through the processes, then we're denying them the opportunity to see patterns. Okay. And you see patterns when you do a lot of reps with something. And you go, oh, I can take that shortcut. Oh, I can take that shortcut. And that's how this all developed. A lot of repetition. All right. So I think we got to build in repetition into courses and mathematical courses, which is why I introduce an awful lot of material early, and then just in a mastery model, stick with it and give credits to students when they finally figure it out. So just some thoughts on teaching. And so I'm going to include a paper I wrote in 1998 with this video when I first started thinking about this. The graphing calculators came in early 1990s, and maybe it was the late 80s. I can't remember. Getting old here. But I saw these nice little curvatures, you know, a little movement of the early technology. And I just thought to myself, if the machine can do that, and we built the machines, then we should be able to do it too. And so I just started playing with the stuff, and this is what came out of it. And so it's a graphing template. And if you learn it in one place and you stick with it, you start to gain some insight. And if you start to plug numbers in and play with numbers with those calculations, you start to get some experience with numerical trajectories, which I think are extremely important. Otherwise, I don't know if you have a feel for a calculation. And if you got to use these calculations as rate calculations in a calculus class and the area under the curve as accumulating amounts, well, if you can't graph the curves, I don't know how you do a calculus course. Right? And that's why I think, you know, people drop out. Don't know what, they've got a bunch of things written down, but can't connect it to anything. All right. And I think you can connect all of high school math. You know, I'm going to say something that might be controversial. A rectangle. Right. I think you can, I think there are ties to it. I think the evolution of the discipline centers around, I mean, listen to some of the language, quadratics, four-sided figure, quad, Latin, four. Cubes. You make a cube out of a bunch of rectangles, you know, and you throw a diagonal in a rectangle and you got a triangle, a right triangle. And it's just endless, right? All the things that come out of this. So just some fodder for the consideration. And, feel free to tell me I'm off track or on track. That I'm enjoying some of the things I'm reading. And I probably should respond to more, but, let's see what this does and see if it, percolates some discussion. All right. Have a good one. Toodaloo. There we go.